Thank you, Gilbert. Okay, so yeah, the fancy formal title of my dissertation is Generation of Compiler Backends from Formal Models of Hardware. I think a snappier title is Generate Compilers from Hardware Models. This sounds a lot more like a call to action, which is what I see my dissertation to be. It's a call towards a specific way of building compilers, plus my experience practicing what I preach. And acknowledgements are going to come at the very end, but none of this work could have happened without all of these people that I've worked with throughout the past 6 years. Thank you to all of you. Seriously, this has been the joy of my life. So this is a compiler. What does a compiler do? Also, I don't think my animations are as snappy as Zach. Don't get too excited, but there's some fun ones in here. So what does a compiler actually do? In general, compilers translate high-level, human-readable, human-writable code down to low-level code executable by a specific machine. A classic example of a compiler is Clang from the LLVM suite, which compiles high-level human-written C code down to target-dependent machine executable code, in this case, x86 assembly. This dissertation is going to deal with compilers from a wide range of domains. So to capture this variety, we're going to be using 2 additional running examples of compilers. Number 1 is going to be the open source deep learning compiler TVM, which was originally developed here at UW. And among many other capabilities, TVM translates high-level target-independent code in a Python DSL down to target-specific code for machine learning accelerators. TVM is going to be the main focus of part 1 of this dissertation. And then Yosis is going to be our second example. Yosis is an open source hardware compiler, which compiles target-independent hardware designs written high-level Verilog. For example, this add, multiply, and design, down to low-level Verilog for a specific hardware platform, in this case, a Xilinx FPGA. Yosis and other hardware compilers are going to be the main focus in part 2 of my defense. So as you can see, compilers are crucial in a wide variety of domains, from deep learning to general CPUs to hardware design. But as we're going to see, even across domains, compilers have a very similar internal structure. So what do compilers actually look like on the inside? Well, internally, a compiler is composed of a few layers. You've got a compiler frontend, which reads code from some front-end language. You've got a middle layer doing target-independent optimization. And then in the end, you've got some kind of compiler backend, which does target-specific optimization and code generation. That is, modifications that are specific to the hardware that we're generating code for. So compiler backends specifically are the focus of my work. That's going to be the focus of this talk today. So just the compiler backend portion of a compiler. So a compiler backend is responsible for producing machine code, which is eventually going to be run on some machine. Whether that machine be a CPU or an accelerator or an FPGA, there are many different target machines. So how exactly does a compiler backend produce target-specific code? Well, if you're familiar with compilers, then you already know that internally, compiler backends are implemented using a set of core algorithms. Again, a classic example in the field of general purpose compilers like Clang is the algorithm called instruction selection. And instruction selection is a stage at which Clang is deciding how to implement each C expression using x86 instructions. So for example, it is this algorithm that decides to implement the multiply expression that's found in that square program at the top using the x86 imul instruction found in the compiled code at the bottom. As another example of a core compiler algorithm, TVM relies on a very similar algorithm to instruction selection called tensorization to determine how to compile high-level operations, such as the matrix multiplications comprising a 2D convolution, down to accelerator calls. For example, this accelerator-specific general matrix multiply operation. And as our last example, Yosis relies, again, on a similar algorithm to instruction selection called technology mapping to determine how to implement subcircuits within the design using FPGA-specific hardware primitives. In this case, a specialized unit called a DSP. So as we can see, compiler backends are implemented using some set of core algorithms. It's different per domain. Drew, you gotta mute yourself. Drew, please. What? Yeah, maybe. Okay. Drew. Okay. Hope we're good.
Nice organizing skills.
Just beg people to do it. Okay, so compiler backends are implemented using some set of core algorithms. For example, instruction selection, like we saw, tensorization, and technology mapping. But how are these algorithms themselves actually implemented? Well, when we dig in, what we find is that embedded within a compiler backend's core algorithms are models of the target hardware. And this is really core to my story. Okay,
Gus, can you check the code?
yeah, I can. I'm gonna have to stop sharing and stuff. A second. Zoom is so frustrating. I can just mute all. There we go.
If people have questions, that might be.
They can unmute. They'll just unmute themselves.
Okay.
Hopefully Drew will not unmute himself. Drew's a good friend. He's great.
Someone can monitor chat as well.
Oh, true. Can somebody monitor chat for me? Thanks, guys. We're off to a great start here. This is wonderful. Okay. I think we're all good. So, yes, so this is really core to the story here. So let me step back. So embedded within a compiler backend's core algorithms are going to be models of the target hardware, the hardware that we're targeting. That is, in order to compile to a specific hardware target, the compiler backend has to have some ideas of the features and properties of the hardware it's compiling to. That is, there's no way to produce code for a target backend without having some kind of model built into the compiler itself. So the way that this is actually implemented is by building models of the target hardware into the various algorithms within the compiler. Let's take a look at a concrete example. Consider Clang's instruction selector that we just talked about briefly. To implement its instruction selector, Clang relies heavily on inbuilt models like this one. This model is capturing the x86 instruction set and is quite literally a list of the instructions that are implemented by the x86 processor, while that Clang is targeting. So Clang's instruction selection is actually relying directly on this model to implement instruction selection. That is, it's actually reading this list of instructions, and it's using this list to know what instructions are available for selection. So we know that compiler backends are implemented using a set of core algorithms. We know furthermore that embedded within a compiler backend's core algorithms are models of the target hardware. For example, the list of x86 instructions embedded within Clang. However, not all models and algorithms are built the same. In comparison to Clang's instruction selector, let's now consider Yosis's technology mapping algorithm and the models contained within. This is a snippet of Yosis's technology mapping algorithm for Xilinx FPGAs. You don't have to understand this code. Unlike the explicit model of x86 instructions in Clang, the model here is a lot harder to actually understand. Like, can you tell what this code is doing necessarily? Thankfully, the developers included a helpful comment describing the code, which reads, if post adder and preg are both present, match for a mux cell driving the C input, this indicates an accumulator situation. You don't need to understand what that means. What I want you to get out of this is that this code is essentially searching for a specific pattern of hardware. And that pattern of hardware they actually helpfully visualized in this comment itself. So unlike the explicit list of x86 instructions inside Clang, this model of hardware that they visualized here is actually encoded within the algorithm itself. That is, the model is not separate from the algorithm. The two are the same. In a bit, we're going to discuss the consequences of this style of implicit model. But for now, let's just directly compare these two models to really drive the point home. So as we've seen, the Clang model of the x86 instruction set is explicit. It's separate from the underlying algorithm, and I'm not actually showing the underlying algorithm here, the instruction selector itself. Meanwhile, Yosis's model of the FPGA is implicit. It's encoded within the search algorithm itself. That is, the model and the algorithm are one and the same. Now, with regards to the underlying algorithms, Clang's instruction selection algorithm is adaptable to new instructions. That is, if we were to add new instructions to the model, the algorithm wouldn't actually need to change. It would just be able to use those new instructions that were added to the model. The technology mapping algorithm, on the other hand, is inflexible to new FPGAs. So if you were wanting to retarget this technology mapper to a new FPGA, you'd basically need to rewrite the entire search procedure, again, because the model and the search procedure, the model and the algorithm are one and the same thing.
So, Gus, isn't there a parallel here between this and the DSL compiler example that you gave, where you expand from some high-level operators to lower-level implementation of that, like, if you're matching a convolution to the actual implementation of some more general language, isn't this a direct parallel to that?
Sure. Yeah, but is there a specific thing that you're thinking of here?
No, I was just saying about if there's any difference that I might have missed, so.
No. I think you're on the mark. I think the question is, how are you doing the matching? Actually, that's all of part one is going to be all about that. The question is like, how are you doing the matching? Are you writing an explicit matching algorithm, or are you simply declaring the features of your hardware? So for example, declaring the instructions that your accelerator implements, and then having a general purpose algorithm that can read those instructions and match, see that your thing can do a convolution and match it to the convolution.
Got it. That makes sense. And how about the model being implicit? Isn't the same? Like, can imagine in the DSL that for high-level operators are using it in the DSL, I'm going to declare what they do using an implementation, where in that case, the implementation of that operator is the same as the model what it's computing. So is that there's similarity there too?
Yeah, I think so. I guess I see what you're saying. I generally, for the most part, we're generally viewing at least in the TVM example, we're seeing operators kind of as black boxes, and then we're going to map them to accelerator calls or something like that. So how they're actually implemented under the hood is not as much of a concern.
I see.
Yeah, but I think,
and not just trying to label things, trying to understand, because that implies a lot, like, I guess, has an impact on the level of complexity of this search too, right?
Sure. Yeah, and I think in part one, there should be like ways to follow your question more deeply, especially with the quality saturation stuff that we do, because we consider like there are many possible ways to represent a kernel, and that's a big part of part one. Okay. So let's keep going. So high level takeaway here, we have an explicit model. Model and algorithm are separate. On the bottom, we have an implicit model. Model and algorithm are the same thing. To plot this visually, we can put what I'm calling model explicitness on the x-axis and what I'm calling algorithm adaptability on the y-axis. Yosis's technology mapping model and algorithm are both implicit and inflexible and are thus closer to the bottom left, while Clang's instruction selection model and algorithm are more explicit and more adaptable. And so they're up towards the top right. Whenever you see a plot like this, you should kind of know what's coming next. Our core argument is going to be that up and to the right is better. That's what we're going to be trying to do. So specifically, the thing that we're going to be arguing is that more explicit models and more adaptable algorithms will produce better compilers. So this takes us directly to my thesis statement. So my thesis is that automatically generating compiler backends from explicit formal models of hardware enables optimizations, improves correctness, and reduces development time. We're going to refer back to the components of this thesis very frequently. So to kind of give us a nice shorthand, we're going to just label them. So my thesis presents two inputs that we're going to be manipulating to produce better compilers. Those are the algorithms that we use to generate and power the compiler backend, and then the models on which those algorithms depend. And then we have three outputs that we will measure to judge the quality of our output compiler backend. And that's the optimization ability, correctness, and development time. And note that correctness and development time here can both refer to correctness and development time of the compiler itself, so the correctness of the compiler, how much time it takes to build the compiler, or any correctness and development time improvements that come from the compiler once it's built. Okay, so I'm going to demonstrate my thesis in two parts. In part one, I apply my thesis to the domain of deep learning compilation in a project we call Glenside, which utilizes more adaptable algorithms, but doesn't necessarily improve on the state of the art when it comes to model explicitness. In part two, I more fully realize the thesis in the domain of hardware compilation for FPGAs in a project called Lake Road, which combines both more adaptable algorithms and more explicit models. Finally, I'm going to talk about, very briefly, ongoing and future work called Church Road, which combines a lot of the ideas from the two parts. So this is, actually one more slide. Lastly, before we really jump into the content here, I want to mention that a lot of these ideas are not new. In fact, the automatic generation of correct compilers has been a holy grail. It's a big research topic, and it's been a thing since the mid-90s and before. So there are really two frontiers along which my dissertation is advancing the state of the art, and two things that I really want to point out that sets this apart. First is that, so two frontiers. First is that unlike prior work, which mostly focuses on compilers for general purpose processors, we are going to focus on domain-specific compilers, which makes the task of compiler generation a lot more tractable. That's basically what made this work feasible. And second is that we're applying off-the-shelf algorithms like quality saturation and program synthesis, which have grown steadily more powerful throughout the years. And by focusing on domain-specific compilers and using powerful off-the-shelf algorithms, I do believe that we're going to be able to achieve the dream of automatically generated compilers. That's the hope. Okay, so this is actually a good place to stop and take questions on intro stuff if we have any. I'm going to take a drink. Okay, no questions?
What sorts of workloads or benchmarks are you using?
Yeah, so it's going to be different for both. So part one is going to be a lot of machine learning workloads. And part one was done many years ago before the LLM boom. So it's going to be a lot of old machine learning workloads. So I apologize for that. Part two is going to be a lot of hardware designs. So like specialized hardware designs.
So you showed like two axes here, but is there any consideration going on for thinking about another axis for the compiler performance? I don't know, like.
Sure, yeah. So compiler performance is interesting. We take a really coarse view to performance because a lot of the times the work that I'm doing is essentially enabling the coarse grain performance I'm talking about is like discovering ways to use features of hardware that you wouldn't have found otherwise. You'll see that both in part one and part two. It's like, can we find ways to use machine learning accelerators in ways that they haven't been in the past, or finding ways to use units of hardware that just wouldn't have been used otherwise? And so performance, the easiest way for me to tackle performance is just, can you go from like 0 to 1 on some binary of like, this was not used before and it's now used after, as opposed to like, we're, a little bit faster or something like that. So there is, in general though, I would say that performance isn't necessarily an axis on here. It's more a result of pushing your compilers up in this direction. In my thought, a result will be performance. So actually, we go back to here. The optimizations is really what I consider like an output of this methodology. Is if you push up and to the right, one of the things you're getting at is a compiler that is more performant, produces more performant code. Okay. Great. Anything else? Otherwise,
I think
jump
there's a
into-
chat question.
Oh yeah, could somebody read out a chart?
So Akash asked, one of your axes is model explicitness. How does the form in which the model is provided affect the power of your approach? For example, suppose I just gave you the hardware RTL design as a fully explicit view of the machine.
Yeah, so thanks, Akash, for, I don't know if you set that up on purpose. That's exactly what the second half of this talk is going to be. We actually do take RTL. The form that your model comes in matters immensely. Partly because of the engineering effort of being able to interpret that form and do something useful with it. You also have to trust that the model is correct. So if you get RTL, or if you get hardware code that specifies what a piece of hardware does, how do you know if it's actually right? If it comes from the vendor, maybe that makes it more believable, but that doesn't necessarily mean it's correct. So in general, it affects the process a lot. It affects what you can do at an engineering level. It affects how much you can actually trust the model. There's many things that it does affect. So thank you, Akash. Yeah. And if you have like more specific things you're worried about, we can talk about those. Okay, we are very low on time already, so we should just go fast. Okay, so we talked about my thesis. In part one, we're going to show how by encoding accelerator semantics as rewrites and applying a technique called equality saturation, we can generate a deep learning compiler backend which finds more accelerator mappings, improves accelerator testing and verification, and reduces accelerator development time. And just to put the labels from my thesis on here, the algorithm that we're going to be inputting into this is this new algorithm, equality saturation. The models are going to be the rewrites that capture accelerator semantics. And then the output optimizations, correctness, and development time will be the increased mappings, the increased ability to test and verify, and the reduced development time that result. So let's set the scene. For my entire PhD and even before, leading architects have been claiming that we're in a new golden age for computer architecture. And I won't talk about too much about why. And I'm also just appealing to authority here. This is a slide from Chris Latner, who himself is quoting a slide from Hennessy and Patterson, all about how we're in a golden age of computer architecture. Believe them if you don't believe me. Really, why, the reason that we're in a golden age is because with the death of Moore's law and the end of Dennard scaling, we have headed into this realm of specialization via custom hardware accelerators. So these important specialized chips that are driving a lot of the most important machine learning discoveries, for example, underlying all of this is specialized hardware accelerators. However, despite this accelerator boom, compiling to accelerators is difficult, especially at the time when we were doing this work in 2021. This was definitely the case. Compiling to accelerators is difficult. The difficulty could actually be seen just in the literature. So one of my co-authors, Boyuan Huang, in his dissertation, compiled data from a number of architecture conferences in 2021. What he found was that the proportion of designs in the literature that evaluated on full-size workloads, that is, compiled their design, compiled a full, meaningful workload down to their design and ran it or simulate it, was only about 41% of published designs, with a small proportion of those being from academia. Meanwhile, the rest of the 59% evaluated on partial workloads, or they did not evaluate on workloads at all. Based on this data, we can surmise that compiling to full workloads is so difficult that it really wasn't worth doing for most of these publications. However, compiling to accelerators is also crucial for testing. So why is it crucial for testing? Well, let's take a look at the results of compiling some real image classification workloads. Again, this isn't LLM stuff. This is all old CNN stuff, down to some real accelerators. So when we ran the models on CPUs, the reference accuracy on ImageNet was over 90%, and we expected the accelerators to match this accuracy. However, because compilation down to accelerators is so difficult, these accelerators were only tested on small portions of workloads, just on partial workloads, not on full models. So when we actually finally simulated these models on accelerators, we found that their accuracy dropped to a level that was just functionally useless. So the accelerators which hadn't been tested turned out to essentially not work. So we've seen that compiling to accelerators is difficult, but it's also crucial for testing. A natural question at this point is, why is compiling to accelerators difficult? Well, that's a very big question, and we ended up taking 4 years to publish this paper called 3LA, all about those questions. We're not going to talk about most of 3LA. It is not a contribution of my dissertation. It's a contribution of Stephen and Boyuan's dissertations. However, I did focus on one very specific problem within 3LA. So we're going to be focusing on one specific compilation challenge within 3LA, which is the question of, given a machine learning model, how do we actually find places to use accelerators within that machine learning model?
But to be clear, that accuracy drop was because the accelerator wasn't testing, or the code generation for the accelerator wasn't testing?
No, the accelerator itself wasn't tested. So they were using
those. They tend to be fairly, well-defined operations. Why?
So they were doing some like numerical optimizations. They were shrinking bit widths of data types, and so as soon as you get into like messing with numerics,
Okay, got it.
you better be testing, which
That
is
makes sense.
really common in
Yeah.
accelerators in general, right?
It sounds pretty sloppy though, because changing number of presentations without retesting is sound, yeah.
I mean, this is 2021.
I was listening to you were sloppy, by the way.
No, but
The accelerator designers were sloppy, right? That should be part of the spec, right? So
sure. Okay, so the question is, given a machine learning model, how do we find places to use accelerators? If you remember from the intro, this is what we labeled as tensorization. At the time we were developing 3LA, we looked for existing solutions for handling this task, for handling the task of tensorization. One potential option was the deep learning compilers, TVM's Bring Your Own Code Gen framework, or BYOC for short. BYOC allows users to specify exact syntactic patterns which should be offloaded to accelerators, and it then searches for those patterns within workloads and offloads them when they're found. To put this in the framework of my thesis statement, we can consider the patterns that the developer is writing, that the algorithm is searching for, to be the models of hardware. We're capturing models of hardware as these high-level patterns of what the accelerator does. And then the algorithm is the search procedure that's just looking for those patterns and mapping them where they're found. So if we consider where BYOC falls on our model explicitness / algorithm adaptability spectrum here, we can see that its models of hardware are fairly explicit. They're these high-level patterns, but the algorithm itself is inflexible. And why am I calling this algorithm inflexible? Well, what it's doing is it's just searching statically for these patterns within workloads, and we'll take a look at an example of where this breaks. Do you have a question?
Maybe you're gonna get to this, talking about the language that you're matching in.
Mhm.
Are you dealing with loops or not?
In these workloads, no. No
So you're
loops.
dealing with this at like the graph level.
Yes.
Of XLA or.
Exactly. This is all done in Relay. And so Relay you can write loops, but all of our models were just straight line CNNs.
Okay.
Yeah. Questions? Other questions? Okay. So why is this method of searching for these patterns inflexible? Let's just take a look at a concrete example where this breaks. So this pattern is searching for what's called a linear layer, which is just a dense matrix multiplication followed by a bias addition. This is a classic layer in machine learning. Consider this snippet of code, which is directly from the MobileNet deep learning workload. This snippet of code also represents a linear layer. However, it will not be matched by our pattern because this add here should be a bias add. And this sounds really trivial, right? Why don't we just switch the add to a bias add? Does this actually occur in real life? This seems trivial, but these mismatches do occur in real life and they do accumulate. So to demonstrate how they occur in real compilations, we attempted to compile 5 machine learning workloads down to accelerators using BYOC. The 2 accelerators that we're targeting are VITA from UW and FlexASR from our collaborators at Harvard. With the exception of ResMLP and Transformer on VITA, we find very, very few matches using BYOC. And as we're going to see in a bit, it's not because the opportunities to use accelerators are not there. It's going to be because the search algorithm is actually inflexible. So after surveying existing solutions, namely in this case BYOC, they turned out to be inflexible. So
What are the search?
So in this case, sorry, what other search algorithm or what?
What are they?
So they're just doing some kind of standard, like essentially you think of like regex based on a pattern over a program. So you specify a pattern that looks like this. You say, this is the computation that I'm looking for. It then does standard I'm not exactly sure how they implemented the search itself, but they do this and then they mark the places in the workload where they find it. Cool. Okay. So I'm gonna now give an outline for the rest of this section. As we've presented, the underlying problem is that mapping to accelerators is crucial, but current tools are inflexible. Our insight is that a technique called equality saturation can help in this task. And using that insight, we built Glenside, which finds more mappings, improves testing, and eases development overall of accelerators. So let's now move on to our insight that equality saturation can help with this task of making our matching more flexible. So recall the underlying issue here. It's that our pattern won't match when there are slight mismatches in the workload, like this add that should be a bias add. How do we fix this issue? Well, one option would be to change the pattern. You could just change the bias add to an add, right? And then everything's fixed. But this puts extra work on the user. It makes things quite brittle, and it doesn't necessarily account for all of the mismatches that can occur within workloads. There can be a diverse set of mismatches that occur within these workloads. A more clever solution would be to actually rewrite the underlying program itself. So in this case, why don't we rewrite the add to an equivalent bias add operation, producing this code, which the pattern can then match up. That is, we can increase the adaptability of our matching algorithm by including these additional rewrites that aid in pattern matching. So if we throw in these additional rewrites, we can rewrite the underlying workload and find more matches for our patterns. But there's a potential problem with this strategy. So now imagine that we have 2 operations that we're trying to offload to accelerators. So we don't just have our original linear layer pattern. So we have this pattern, but in addition, we have some second new pattern that's matching for some other op followed by an add, not a bias add, but an add. On our original program, the add to bias add rewrite that we are currently using, it's still going to help us out. We're still going to be able to match this pattern on the left with this rewrite. However, now imagine there's some other code in the workload somewhere that is our other op followed by an add. What is this add to bias add rewrite going to do in this case? Well, it's going to, again, rewrite the add into a bias add, and it's going to produce code that our second pattern can no longer match on. So that is, while this rewrite makes our first pattern work, it actually breaks our second pattern. So the fundamental problem that's happening in this case is that we're forgetting the old version of the program. That is, when we rewrite the add to a bias add, we forget that there was ever an add there in the first place. So a big question is, can we keep both versions of the program around? Can we keep both the add and the bias add version of the operator? And unsurprisingly, the answer is going to be yes. We're going to be using this technique called equality saturation. And the basic point of equality saturation, or the key insight of equality saturation, is that we can keep all versions of the program that we've seen so far. So in this case, when we're firing and I'm going to start using AST representations because it'll make this example a little easier. Sorry for switching in the middle here. In this case, instead of destructively rewriting our add to a bias add using this rewrite, so that our second pattern no longer matches in this case because the add is no longer there, what we're instead going to do is we're going to keep the add around and add the bias add when we fire this rewrite. So now we have both the bias add and the add node. Our second pattern can still match, our first pattern can still match, and everything is good. Under the hood, we're going to use a library developed here at UW called egg for its implementation of equality saturation. Okay, so great, let's use equality saturation. I'm looking at time here and I don't have much, so I'm going to speed through a lot of the unimportant stuff here. Basically, a big contribution that we did in this work was current deep learning IRs were not equality saturation friendly. That is, there was no language that you could use to both represent the workload you're trying to match over and run equality saturation on. And so a big contribution that I'm unfortunately just going to have to speed through was a technique called Glenside. So we developed this thing called Glenside, which is a pure low-level binder-free tensor IR. Essentially, you should read that as we developed the language that you could both use to represent machine learning workloads and do equality saturation on. Yes.
Is this a generic approach to avoiding the binders, or is this specific to tensors?
It's specific to tensors. Yeah. It's specifically like a new representation for tensors that allows you to redefine operators in a way that other IRs often have you using lambdas to specify, for example, like what dimensions you're operating over in a tensor. And what access patterns do is they kind of bake that into the type system itself. So there's these operators that allow you to specify essentially which dimensions are important and which ones are not, which ones should be computed on and not. Good question. Yes, Stephen.
At risk of getting into the weeds, do you think your approach to representing tensor operators without binders, do you think that will generalize to tensor operators that people are using these days? I know in Glenside, we looked at only a few models, right? So, like dynamic shapes, for example, are commonplace these days in LLMs.
Yeah.
Does Glenside have an answer for those?
It doesn't have an answer in its current implementation because we stopped working on it many years ago, but there's no reason for me to believe it wouldn't work. And in fact, in a different life, I would have kept along the Glenside direction. And I was actually very excited to start handling a lot of these things. I don't think there was no reason to suspect that you couldn't keep extending this idea to handle dynamic shape, to handle, for example, one thing I really wanted to do was handle different layouts, be able to easily relay out a tensor. So there's no reason to believe that it couldn't do those things, in my opinion. Other questions? Okay, so again, with time in mind, I'm going to keep moving through this. This is just about how the actual underlying representations. You should just read the paper if you want to see more about it. So what we did then was we built this thing called Glenside. We could use it to do equality saturation. So then we integrated it into this larger 3LA tool to implement more flexible tensorization. Essentially, what we did was we captured accelerator semantics as rewrites. So this is our linear layer captured as a rewrite. You can see we're looking for a dense followed by a bias add. We map that to an accelerator call. But then on top of that, where we go beyond BYOC is that we also add all of these general purpose rewrites over Glenside that allow us to enumerate a much larger space of equivalent tensor programs that potentially expose new places where we can use our accelerator. And that's exactly what we're going to see. So I'm going to skip to the results here. And so if I skip to the results, remember that BYOC failed to find a bunch of mappings across a bunch of these workloads. And what we find is that we increase all these mappings using Glenside, which is great. We also, in the end, we also help improve correctness. So using Glenside and 3LA, our hardware designers were able to iterate on this. Remember these broken designs, and able to bring the accelerator accuracy back up. And then I'll also just defer to the paper for talking about development time and how 3LA should be used in the process of developing hardware to speed up development. So in summary, in part one, we showed how by encoding accelerator semantics as rewrites and applying equality saturation, we can generate a deep learning compiler backend which finds more accelerator mappings, improves accelerator testing and verification, and reduces accelerator development time. So represented visually, what Glenside and 3LA did was they improved upon algorithm adaptability of TVM's Bring Your Own Code Gen framework by utilizing a more adaptable algorithm, which was equality saturation. But note that we didn't actually improve on the state of the art in model explicitness. So we really just moved up the y-axis here. And we're going to talk more about this in part two. So I'm going to leave this up as I asked for some questions on part one. Yeah, go ahead.
On your map on the last slide.
Yep.
Is Clang instruction selection gonna happen?
No, we just focus on specialized, like on domain specific things. Maybe a bit of a red herring to include Clang selection here. Other questions on part one? I know that was kind of a fast move. Okay, cool. Let's move on to part two. So, yeah, so in part one, we showed how we can increase algorithm adaptability by introducing this new algorithm, equality saturation. In part two, we're going to more fully realize the thesis via a project that I called Lake Road, which is going to both increase algorithm adaptability by introducing another new algorithm and also increase model explicitness. So again, to remind you of my thesis is that automatically generating compiler backends from explicit formal hardware models enables optimizations, improves correctness, and reduces development time. In part two, what we're going to show is we will show how by applying program synthesis using semantics extracted directly from FPGA simulation models, we generate a technology mapper which discovers more DSP mappings, provides stronger correctness guarantees, and produces more extensible compilers. And just to map this to the ideas within the thesis, the input algorithm that we're going to be introducing is program synthesis. The models are going to be the semantics that we extract directly from FPGA simulation models. And then the outputs are going to be optimizations, correctness, and reduced development time in the form of Lake Road's greater completeness, correctness, and extensibility. Okay, so I'm now going to go back and give some background on FPGAs and what FPGA compilation means. So this should be a complete reset from ML compilers. This is very different. High-level ideas are the same, but we're going to step into a completely different world. Okay, good to go. Let's go. So FPGAs, or field programmable gate arrays, are a reconfigurable hardware platform. They're a platform that you use to produce other hardware. They're reconfigurable so that you can program hardware on top of them. Internally, FPGAs are composed of small hardware primitives. For example, lookup tables that you can use to implement logic functions like AND or, registers which hold state, and then digital signal processors, which accelerate. They're specialized units that accelerate things like arithmetic and have many other features. A key step in the process of compiling an input design, for example, in high-level Verilog, down to an FPGA is called technology mapping. Technology mapping involves choosing a subset of the hardware primitives such that they implement the input design. So to produce an optimal compiled design during technology mapping, it's crucial that we utilize all the primitives on the FPGA, especially taking care to use specialized primitives like DSPs. However, what we found is that while mapping designs, state-of-the-art technology mappers do not efficiently use all the primitives available on the FPGA. For example, imagine that this design could be implemented using a single DSP if the DSP was configured in a correct way, so one of these specialized programmable units. The state-of-the-art technology mapper from Xilinx might fail to discover this mapping and instead map it using additional LUTs and registers. This leads to a larger, slower design in general. So in response to this discovery that state-of-the-art tools do not efficiently use primitives, we built a technology mapper that we call Lake Road. Lake Road is powered by our core insight, which is that configuring programmable primitives like DSPs is similar to writing programs. So use a technique called program synthesis. If you don't know what program synthesis is, don't worry. We're going to talk about it a little bit later in the talk. Applying program synthesis to technology mapping produces a technology mapper which is more complete than existing tools. That is, it finds more opportunities to map using specialized primitives and overall produces smaller designs, while also providing stronger formal correctness guarantees and being more extensible than existing tools. This brings us to the overview for the talk. The problem that we're addressing is that existing tools fail to utilize program primitives. Our insight is that when mapping to program primitives, you should apply program synthesis, and also you should extract semantics directly from Verilog. We use this insight to build Lake Road, which is more complete, more correct, and more extensible than existing tools. To use the labels from my thesis, the more flexible algorithm we're introducing here is going to be program synthesis. The hardware models the algorithm relies on are the semantics that we extract directly from Verilog. The optimization, correctness, and development time improvements all come from Lake Road's greater completeness, correctness, and extensibility, respectively. Okay, this gives us a roadmap for the talk, so let's jump right into the problem. We claim that state-of-the-art tools fail to use existing primitives efficiently. Let's dig into exactly what we mean by this with a concrete example. So let's imagine a hardware designer is trying to compile this design, which is simply an add followed by a multiply followed by another add, onto a Xilinx UltraScale Plus FPGA. The Xilinx UltraScale Plus FPGA architecture contains plenty of LUTs and registers, but for maximum performance, our hardware designer is instead aiming to use the architecture's specialized DSP primitives. They know that if programmed correctly, the UltraScale Plus's DSP, which is called the DSP48E2, can efficiently implement their design. That is, if the DSP is programmed to select the pre-adder, the multiplier, and then the post-adder, it will implement their add, multiply, and module. Thus, we would expect that we should be able to implement this entire add, multiply, and module just using a single DSP on our FPGA. However, when we actually attempt mapping with Xilinx's proprietary state-of-the-art compiler, we find something odd, which is that the compiler produces a design which does in fact use a DSP, but it also uses additional LUTs and registers, which are completely unnecessary. And if you think that this seems like a toy example, people are posting online about exactly this problem. So it seems to be a real issue that people care about in the hardware development community. So state-of-the-art tools have failed us. Now what? Do we just give up and accept suboptimal results? Well, if we don't want to give up, if we don't want to accept suboptimal results, there's really only one option that remains, which is to manually instantiate the DSP. And by manually instantiate, I mean that the developer will actually have to handwrite the low-level Verilog that instantiates the DSP in the exact configuration they care about. And in this case, this is an example of the Verilog that they would have to write to do this. You don't have to understand Verilog to see how unpleasant this would actually have to be, how unpleasant this would be to do by hand. Each of these lines represents a separate port or parameter that the designer has to understand how to set by reading the manual for the DSP, which itself is 75 pages long and is really unpleasant to read, as both Vishal, Andrew, and I know very well over the past year plus. The manual itself internally is describing complex interdependent constraints on dozens of ports and parameter values, which makes determining a valid DSP configuration quite difficult.
Even the manual is generated directly from Verilog.
People talk, I mean, this is a thing that people do. The architecture community cares a lot about PDF to Verilog this is something that has been talked about.
But they mostly use Verilog to PDF, right?
Yeah. I mean, it probably would work, honestly. Okay. Other questions while we're still? Okay. So even once our designer has written this by hand, they have an implementation that uses a single DSP, but they still have no formal guarantee that their implementation is correct. They can attempt to catch bugs via testing and via simulation, but they have no way of knowing that there's not some bug that was in some edge case that's buried somewhere in that 75-page manual. So to recap where we are, state-of-the-art tools failed to produce an efficient mapping. It cost our designer a lot of time and effort to actually produce this mapping manually, and in the end, they don't even know if their output is correct. But let's take a step back. What did our designer actually do to produce this implementation? Well, what they had to do was write a bunch of somewhat esoteric Verilog. They had to consult extensive documentation to do so. The documentation, it documents what combinations of ports and parameter values are legal and which ones aren't. And as I'm describing this process, it's kind of fair to compare this entire process of configuring a DSP to writing a program in a domain-specific language that's embedded within Verilog itself. So the claim here is that embedding or configuring a DSP is like writing a DSL embedded in Verilog. So this brings us to our primary insight here, which is if configuring DSPs and other complex programs is similar to writing a program, we should use a technique from the field of programming languages called program synthesis. And just to tie this to our thesis, choosing program synthesis is our way of increasing algorithm adaptability here. So we're going to now turn our focus to the implementation. I'm going to move through this quickly. We're already at 2, so I'm going to really try to wrap this up.
There is a question in the chat.
Oh, great.
Noah asked, has anyone used constraint logic programming for this?
Oh, that's a great question. I don't know about specifically constraint logic programs.
Specifically for DSP configuration.
Yeah, you did write our related work section, so you would know. Not that I've seen. So, okay, so there's the hard part about a question like that is you don't know what major tools are doing because they're proprietary. There is, after AskBloss, somebody sent me a tool that is doing something with constraint solving. So I know that it's at least on the radar. Like CSP specifically, I don't know if that's being used, but yeah. Thanks, Noah, for the question. Yeah.
Maybe for the broad audience, can you translate constraint logic program?
No, I don't know the details. I think we read a paper on it years ago, but I don't remember anything about it. Can you? It's some specific
Answer set programming. It's like Prolog with with theories.
right. I feel like we went through a answer set programming phase years ago, thanks to Remy. Yeah.
Thanks.
Yeah. Questions? Other questions?
There's another one, but I believe it will be handled soon.
Great. Let's
And we'll
zoom
come
on.
back if it's not.
Okay, so trying to decide what's important here. I think I'm going to actually not talk too much about how program synthesis works. So apologies. I think I just want to get to results. So Laker takes a design, produces an implementation. I'm going to skip over internals here, but essentially we're using a thing called a sketch guided program synthesis, which uses a constraint solver to fill in holes in a sketch, and you get out a concrete implementation. And the really nice thing here is that you get a correctness guarantee because you're using this solver under the hood. And we are using Rosette to implement this, another UW produced tool, another UW Pulse produced tool. So we don't have time, again, like I said, to dive into implementation here, but there's one technical detail that's really important to my thesis. This actually kind of brings one specific part of the thesis altogether. And that is this point, which is that solvers don't actually understand Verilog. The solver doesn't know what a DSP instantiation means. So how do we tell the solver in its language, a very low level, language over bit vectors, essentially, what this instantiation of a DSP actually means? Well, luckily, Xilinx releases models of all of their primitives, and these massive Verilog files encode the exact functional behavior of the primitive. These are intended for simulation. These are intended for once you've compiled your design to hardware, you can now simulate it to check that it works. At the same time, these are exactly the type of explicit models that my thesis is referencing. I mean, how can you get more explicit than the actual hardware definition of the primitive that you're trying to compile to? So these are the types of models that my thesis is very specifically referencing. So Lakecode introduces a technique that we call semantics extraction, which uses the open source hardware synthesis tool Yosis to convert these Verilog vendor provided simulation models into semantics comprehensible to the underlying constraint solver. And I just want to emphasize the importance of semantics extraction from Verilog for the thesis story. So in part 1, we showed that we can push up the y-axis by introducing a new algorithm, equality saturation. But we didn't really move the needle on model explicitness. With Lakecode, we can more fully realize our thesis by both introducing program synthesis, but also introducing this idea of extracting semantics directly from Verilog. So using program synthesis is what increases our adaptability, but using semantics extracted directly from Verilog increases the explicitness of our underlying models.
Can I ask a question?
Yes.
Can you maybe bring what you mean by semantic expression? We do have a different IR.
So it's we're actually producing essentially like SMT-lib expressions. So you can really just think of it as Verilog to SMTlib. It's a little, it's more like Verilog to Rosette. But we're just essentially taking Verilog, which is already just bit vector expressions. It just looks different because it's in hardware world. And we're converting that into, something that the solver can actually understand. Yeah. Questions? Other questions? Okay, yes.
One really quick note on the graph again.
On
Can you briefly talk about, so I get algorithm adaptability as being explicit things, and model explicitness is good for getting correctness guarantees. What's the,
So both of these things are ideally going to help with, optimizations, correctness, and development time. They should all feed into both. I mean, algorithm adaptability is kind of the idea that your algorithm should adapt to new hardware. The model explicitness is also kind of key to these things are a little more tied than I'm making them seem here, because the model explicitness is essentially how you adapt to new hardware, right? You need to capture your hardware in some explicit form, whether it's the list of x86 instructions, whether it's your, Verilog definition of your hardware primitive. The more explicit that model is, the more you can kind of take it as an input for your algorithm. Okay, well, yeah.
Ratish is asking, they point out the Xilinx model also has many parameters. Are these parameters also exported out from Yosis?
Are they exported out from Yosis?
So I assume all those ports and parameters from that you had to convert.
Yeah, so Ratish, you might be touching on something that's really interesting here, which is there's a specific thing you have to do when you're extracting semantics from Verilog. It's kind of an engineering level detail, but also a headache, as Vishal has known over the past entire quarter. You have to convert parameters into ports so that they don't get simplified to constants. It's a whole thing. We can talk about it offline. I think that's probably what you're asking. But in general, we are able to export those parameters as runtime modifiable ports so that we can actually do synthesis over them. So short answer is yes, we can synthesize over all ports and parameters. Sorry, I shouldn't say all. We can synthesize over most ports and parameters based on some Verilog semantics things. But we can talk about this offline. It's a great question. Anything else from the chat? Okay, cool. So yes, I just wanted to emphasize here that it's really the semantics extracted from Verilog that pushes us along this x-axis. And as you can tell, it's the thing I'm most excited about. It's one of the coolest things I think I've done in my PhD, so I'm a big fan. But it's hard to get other people excited about it, I've found. Okay, let's do evaluation. So I'm gonna zoom through this. The really important result is that Lakeroad finds more mappings to DSPs than other tools. And this corresponds to our optimizations claim. So going back to our original add, multiply, and example, if you remember, what we did was we ran it through the state-of-the-art tool from Xilinx, and we found that it could not map it to a single DSP. We run it through Lakeroad, we find it does map it to a single DSP. To expand on this, to make a full evaluation, what we do is we first add a new tool. So we also compare against Yosis. And then we also just add a bunch more designs. And so these are going to be our benchmarks that we're compiling. And so what we do to enumerate a bunch more designs is we just look through the DSP manual and we produce a long list of designs that should go onto a single DSP according to the DSP's documentation. So we're just enumerating all the designs that should fit onto a DSP. In the case of the Xilinx FPGA, this produces over 700 benchmarks to run on. We then run all of those through all of our compilers, and we determine, does it map the design to a DSP or does it not? It's a very simple yes or no. So now we plot those results. Let's begin with Yosis. So Yosis successfully maps a very small percentage down here to single DSPs, represented by this small green bar. And the rest, it uses extra resources like LUTs or like registers. On the rest of the benchmarks, for the state-of-the-art tool from Xilinx, it does a good amount better. So it maps about half of these benchmarks to a single DSP without using extra resources. And then in the end, Lakeroad outdoes them both, mapping about 1.5x. And then you'll notice, we always get the question of what does it do with the ones that aren't mapped? So we have the purple bar and the black bar. The purple bar is unsat. This is where Lakeroad has actually technically proven that the design cannot go onto a DSP. So this is an interesting case where either the simulation model is wrong, some of the internal constraints that we add to make synthesis complete may have blocked some designs from being produced, or something else is happening under the hood. And then black is just timeout. So solvers, timeout. You can't always get all of your queries to complete. And so that's that last remaining section.
What's the average compile time for each of these options?
Yeah, it's a really good question. They're way over. We have this in the paper, but we didn't include it because most people seem to not care, surprisingly. So it goes from like Lake Road is around on the order of seconds, like less than 10 seconds. I think it was like 5 seconds to do the query. Yosis is fast. It's like less than a second. And then Xilinx is like 100 seconds. It's like 2 minutes. And it's because
Some search too, right? So
well, and honestly, it's mostly, it's not even an interesting reason. It's just because we're calling Vivado, which is the Xilinx tool, and it takes like a minute to boot up. It's just a tool that like takes a while to start. So
because it's very find the license with Xilinx.
yeah, exactly. Yeah. So we decided not to really include, it's not interesting because number one, people don't care, and it's so noisy.
Well, the reason I asked it, whenever you show timeout to me, they're like, my brain really would like timeout for how long did you wait?
Oh, I do have
waited a nanosecond more, would you have gotten lucky or not, right? So-
maybe on some of these, yeah, maybe on some of these. The timeout, I think the max timeout for this was probably 100 seconds. So some of these are running. I have graphs I can show at the end.
These are all very small examples. Right?
Very small examples. Yeah.
So if we start increasing the size of the examples, then what Luis is saying would be very different. Or what he's asking about would be very different. It's not.
Oh, sure. Well, I mean, the real answer is you would just essentially you get to a place where, at least for me, using this, from an engineering perspective, you'll get to a point where the timeouts are you just assume it's not going to complete and you need to do other things too.
What I mean is, if you take Luis's question as one about how does time taken, compile times, how do those vary across problem size,
Mm,
then there would be something that you'd see interesting, right?
So,
Comparison.
I mean, it depends on how you're using Lake Road on a larger, I think it gets complicated because it's like, how are you using Lake Road on a larger problem size? That's a big part of the Lake Road story is that program synthesis is like this really powerful machine that you have to apply to really small problems. And maybe that's an unfair characterization. In my experience, that's how it works. So you almost don't, I am not really a fan of pretending like you could scale this beyond single DSPs, which is what, that sounds bad, but future work is like why I'm trying to handle this in future.
But you could have an outer loop that decomposes the program into smaller units.
Exactly. Yeah, exactly. And that's exactly what Church Road is.
Even then, the scaling question could be interesting, as we're saying. Well, the reason Xilinx takes a long time is because it has to boot up.
Mhm.
But if it boots up and then it runs through the equivalent of 10,000
Yeah.
small problems, right?
Yeah.
Then, okay, that possibly amortized now.
Definitely. Yeah.
We also have a couple of questions in chat.
Let's do it. This is really the most important thing.
So Scott asks, what bit widths of operands were you using in these specifically for Vivado?
We go up to 18 bits wide. So we go up essentially to the widest operations with asterisks on it, the widest operations that will fit on the DSP via the multiplier. So this is DSP 4082, the multiplier is 18 bits wide, so we just go up to 18 bits.
How small do you go?
I think down to 3. Thank you, Andrew. Yeah, down to 3. So
Okay.
we did go down. We went down to 1, and we started finding the tool started producing incorrect compilations, which would have been an interesting part of our story if we had time to integrate it. But yeah, compilers did not like 1-bit multiplication, it's turned out, which is kind of surprising. But yeah.
Last part of this. So did you find that Xilinx, that the fraction of the time Xilinx used the multiplier was very high for high bit widths and non-existent for low bit widths?
Well, so, okay, so that's a good question. So the way we structured this eval was that for Xilinx specifically, we did everything we could to force it to use the DSP, to force it to use the multiplier, just so that we could ensure that we were giving it the best chance to put it on the multiplier or put it on the DSP, if it could. So I think what you're getting at is essentially, why would you use a DSP on small bit widths, which I think is a completely valid question. I leave that to hardware design experts to determine whether that's, when to switch from using the DSP versus implementing with LUTs and carry chain. am I interpreting the question correct? Is that the like subtext here?
Nope, actually a little differently. So I predict if you look through your data
Uh-huh.
and you look and you graph the Xilinx usage of DSP versus the bit width of the operands,
Mhm.
you'll find that something like below 10 bits, Xilinx never uses the multiplier, and
Hmm.
above like 10 bits, it does.
Okay.
And so does that mean that your bar for Xilinx soda here is actually not how well it uses the DSP for functions, but is a choice they make that they'll never use it for below 10 bits? And it'd be
Yeah, no,
interesting to see the distribution.
so I don't have the distribution on me, but I just looked through it last week for a different reason. It isn't that. It's actually it's a weirder pattern. It's actually at every bit width, certain numbers of pipeline stages don't work with some regularity. But it will, if we put the like Xilinx specific annotation on the Verilog code, it will always put it on a DSP if we want it to. Like it seems to obey that request. But it's specifically the number of pipeline stages that really seems to mess with it a lot of the time. Pipeline stages, and then what the post adder is doing. If it's doing add or subtract, also seems to mess with it.
Makes
But I
sense.
see what you're saying.
Makes sense. Thanks.
Okay, yeah. Let's.
Mike also has a question, but I think we can take it at the end.
Okay, yeah, I'm gonna skip through the rest of this. Our results extend across a bunch of different FPGA platforms, which is great. So Laker does well on all these FPGA platforms. That was our completeness claim. In terms of correctness, we provide stronger correctness guarantees because we use program synthesis. Other tools aren't giving any correctness guarantees, so that's kind of an easy win there. Extensibility, we show that we can support primitives across a wide range of FPGA architectures. So we're more extensible. With that, we're going to wrap up part 2. In part 2, we showed how applying program synthesis using semantics extracted directly from FPGA simulation models, we generated a technology mapper which discovers more DSP mappings, provides stronger correctness guarantees, and produces more extensible compilers. This is my thesis statement one last time, and visually, if we want to take a look at what we did in this in my dissertation. In part 1, we introduced Glenside, which improves upon the algorithm adaptability of existing tensorization procedures. In part 2, and we did that using by employing equality saturation, and that resulted in a tool that finds more accelerator matches and improves the debugging experience. We then improved upon both model explicitness and algorithm adaptability by employing program synthesis and semantics extracted from Verilog. This produced a tool which produces more DSP mappings and gives stronger correctness guarantees. I will not talk about Church Road, even though I wanted to. This essentially combines a lot of the ideas from Glenside and Church Road into some of the questions that you guys were just talking about. So how do we scale up to larger designs? And that's what I'm going after with Church Road. I'm going to leave the slide up. And with that, I am done with the technical part of this defense. Thank you. So now is the time for questions. I'm going to do acknowledgements next, but I want to do technical questions first. We'll do acknowledgements very quickly, and then we'll kick everybody out. So any technical questions from non-committee? Yes, Stephen.
Maybe this is a bit obvious, but we're dealing with compilers of different varieties, and something people care about a lot when you're dealing with a compiler is the performance for some value of performance. It could be speed, it could be power efficiency, and performance of the generated code. I don't think we have talked about this very much now in this presentation, that is. So my question is, when it comes to searching for opportunities to apply either accelerators to DSP, how do you know you're using these things well? Or another spin is another goal you can take also is this your problem from the perspective of your thesis?
No, it's a great question. I mean, I feel like you did partly answer the question with that second question, which is great. So thank you. So yeah, it's a very good question. So I feel like I generally kind of cheated on this question of optimization because I generally chose domains where more mappings should almost always imply a better outcome. So DSPs especially, it was fairly clear in most cases, especially like as Scott was talking about, higher bit widths. If you can get your design onto a DSP, in general, it's going to be better. Scott, I know that that's not, I know that that's maybe a blanket statement, too strong of a blanket statement, but in general, like if we can find the opportunity to use the DSP, we should take it. The second part of your question of like, is this the problem? Is this my problem? It's a great follow on. Why wouldn't you, give the opportunity to use the mapping if you can? I guess the question would be, if it's hard to find the mapping, why take the time to find it? So that is a question. I do think in some sense it is our problem, because if I'm producing techniques that cost a lot to actually run, then it's not worth it to find the mappings. But in general, I do believe that like giving the opportunity to produce to use the mappings is always going to be better.
So I think this is one thing that, we've talked about in recent meetings, but I wanted to just make it a little bit explicit and get your ideas on it, which is that semantic extraction right now, or this kind of thing I would be saying the hardware models, we're focusing on tasks vaguely analogous to instruction selection, all that stuff, what are other and other things. So would you think this type of
Yeah.
are going to be super useful?
Okay, so inside of Verilog is a strange, expansive language. There's a lot inside of it. And one of the things that I would really like to understand more is like there's these timing statements inside of Verilog. You can kind of describe the various timing behaviors of your modules. It would be really interesting to see if can we pull more than just the functional behavior from the Verilog? Could we also pull timing behavior, specified in these, captured in these like timing blocks within Verilog? And then can we produce an optimizer automatically? That's kind of that's the obvious next step. Definitely a hard problem. I think frankly, mapping is, I like the problem because it's kind of easy. I mean, it wasn't easy, right? It took years, but optimization is much scarier, but also it's still with a lot of these models, the data is there, the information is there. So that's kind of the next most obvious thing we could potentially do.
Can I try the question, or is somebody else in front of me? Or
No, you're good.
okay, all right. So I'm curious that let's say you succeed in the rest that you wanted somebody else who completes to finish this vision of doing compilers automatically. Do you then still think that compilers make sense? Like, could you also take the program as input or the language spec as input and whatever you want to compile, such that what you take in is, in addition to the algorithm and the hardware spec, you take the language spec and the code that whoever wants to write the user code as input as well. Then you just do the search, do your magic only for the things that the code as input needs, and then compilers become something. It's a just-in-time compiler, not in just-in-time compilation.
But it's still a compiler, right? Like I think philosophically, that's still a compiler.
Well, but philosophically, right. But now, since talking philosophically, it definitely is, right? So would that change how you do things? If you would not produce this intermediate machine called a compiler, what you want to do in the end is just produce the final thing that runs on the hardware whose spec you have in the model, right? So
I mean, I think that you probably would do things differently. It's kind of hard for me to put myself in that mindset, knowing just how much we had to like specialize, like go the opposite direction to get any of these techniques to work. We had to shrink the problem.
Because you had to be general too, right? So
sure. Well, we had to be, I guess, general in the specific. We had to take a domain
in general
and then be general in that domain. So would you do something different? I think at a high level, no. I think you'd be using powerful, off-the-shelf, automated reasoning algorithms. Like that should be the strategy. Take what other people are spending their entire lives making better and apply that to your problem. There definitely would be differences, but I think that the core is going to be like, can you actually, you're saying take the language spec as input, take the hardware spec as input, take the program as input. So we have to, that's kind of implying we already have model explicitness solved. So we have our hardware model explicitness. So you have to find a way to capture all those things. So that's, I think you'd be the same along that axis of keep making everything explicit. And then you'd also be the same along, the y-axis, because you'd just be using off-the-shelf algorithms, whatever most powerful algorithms you could find.
Thank you. Let me ask this question. I don't expect you to have any good answer. To be clear, I think it's a question that's good for everybody to think about, so it's better for me to ask it now. is, it's sort of going off of what Louise said. How do I know how general your solution is? If I'm somebody coming to this and I say, I don't know about this Gus Smith guy, he seems kind of sketchy. Like, what's that sort of adversarial evaluation where you really convince me of that? Like, we did have
oh,
some
yeah.
questions going around, right? Like, well, okay, you have some bars on percentages
Yeah.
of cases that you handled, but
Yeah.
how do I know?
So here's where I think the rubber hits the road. I think it's a great question. I think I've started to care a lot more about this late into the PhD. Thank you, Zach, for making me care about what users actually care about. So here's where it's in, I think.
Or just other academics, right? That's why I mentioned it because.
Well, no, I
every
actually
paper
think
you
it's
read,
tied.
This is a reasonable question, right?
I think they're tied together though. I think the answer's tied. So here's where I think it matters. I think, for example, Dan Petrisco, who's a student of in architecture, came to me and is like, hey, can your tool do this specific thing? Like Xilinx's tool is not mapping this case, and I need this case mapped. So if my tool can do that thing for him, we produce a better design for him. If I can package the tool up such that he could use it without even asking me, we produce a better design for him and hopefully for even more people who find the tool online and start using it. So I guess the core thing that I'm answering, to convince academics, I think you first convince people who do real work. Sorry, that was not meant to be a joke, actually. No, you convince people who are building actual hardware, and then they start using it. They start actually using it, and
Why does that show generality?
why does it show generality? It's a good question. So yeah, I mean, I feel like generality is in the end, it comes down to like the engineering you put in. I think we can make the tool more flexible, more general, but it's always going to kind of be an engineering hurdle to like, how does Lacro generalize to a new FPGA? Well, the tool in theory supports this if you have the semantics, if you write the sketches. But in practice, how general it is how easy is it to do those things?
For instance, with the evaluation you gave, suppose I have two different systems, we're trying to do the technology mapping. In your evaluation, you could come up with evaluations which look the same in terms of the results you presented, but give opposite results based on the selection of examples. And how they stress the two different technology mappings.
Okay, sure,
Right?
sure.
So how do I know that your choice of examples? How do I know how general it is or how good that is at stressing things?
Yeah,
You see what I'm saying?
So in our case, I would say, the way that we would, or the claim I would make is essentially we exhaustively generated all designs, automatically up to a certain bit with some combination of operators. So we just covered the space. Like we didn't select, we weren't being selective about what benchmarks we were
That's a
using.
pretty good answer.
Thank you. So I should stop here. I should do acknowledgements so that you guys can get out. Oh, it's 30 minutes late. Okay, so I'm gonna do acknowledgements.